What temperature? Yeah. No. All right, any questions before we continue? So again, just a reminder, no class next week on Monday, right? You have Memorial Day. So then we'll just do lecture on Wednesday, so probably no quiz next week as well. But then we'll have our regular lab on Wednesday, and then you'll probably get the final as well next week, so you can, it'll be like I mentioned, a take-home final, so you'll have hopefully all of the weekend and then all of week 10 to work on it too as we finish up. So we'll still be covering acids, bases, but we'll cover that. You can work on your exam that week, and then probably ideally turn it in by Friday in the mailbox. And again, we can always do plus or minus a few days if that becomes an issue, but that's kind of the plan for the end. And so, for labs too, so don't forget, next week is our last lab, or at least last official lab. And by that I mean we still have our acid-base lab. And then week 10, I think I mentioned we'll do an easy practicum. So there'll be a small lab manipulation. It shouldn't be too difficult. And then we'll just do checkout. So washing your equipment, making sure everything's there and clean, blah, blah, blah. So it should be a pretty easy week 10 there. That brings us to the end. And again, you'll have week 11 off essentially. So. And then any last minute papers or anything, yeah, just make sure that that's turned in. You'll have all of week 11 to get any missing assignments. Check your grades, check your grades. So like I said, they should be updated. Yeah, I just need to work on tests and test corrections, but everything else should be okay. Obviously, if you turn stuff in this week, I haven't gotten to it. But just double check that the grades are in. But then your Blackboard grade is inaccurate, so that goes for all my classes. So hopefully I'll fix that. Blackboard is kind of a pain. Hopefully I'll figure it out. It's much faster to do it on Excel. At least for me it is. I can't. Blackboard, they're like, set up your grade book. And like last quarter when I tried to do it, I thought I did it correctly, and then it told me that the total was 200%. I was like, no. So, I don't know. Anyways, hopefully I'll figure that out and get that accurate. All right, so let's continue with our intermolecular forces. So a quick recap. So we were looking at these van der Waals forces. So we said those were the weakest because of a temporary dipole. And so we should emphasize too that all molecules have this. So even, if they're polar or if they have hydrogen bonding, so there's still London dispersion forces. It's just, again, if they're the weakest and if other molecules have other forces, then of course these London dispersion aren't as relevant. And so now let's move on to the next type. And so now looking at polar molecules. And so we have our next intermolecular force, dipole-dipole interactions. And so this results from our polar molecules. And so, right, this goes back to our skills of can we identify whether something is polar. So again, typically asymmetrical. And so I think people have gotten pretty good at identifying whether things are polar or not. And okay, once we establish that something has a permanent dipole, then we can say that it would experience this dipole-dipole interaction. And so we can see why that is. So if something is polar, then we're saying that there's some region of the molecule that has a greater electron density, as indicated here by our partial negative charge, and then that leaves our area of less electron density with our partial positive charge. And then of course we can see how these molecules might want to kind of align together. So this is just acetone shown here, but we're going to see how the oxygen is going to be attracted right to that positive. So again, right, just our basic electrostatic interactions are going to drive that. And then this electrostatic potential map is just another way, again, of looking at the regions of electron density. So red being an area of high electron density, again with our negative charge, and blue of less, and again, right, it wants that negative charge. So there's the attraction, and so of course that helps hold it together. And so now we can make some comparisons. So now trying to figure out which one has a higher boiling point. So now we're looking at formaldehyde versus ethane. And so the first thing we want to do is always look at our London dispersion, molecular weight argument. And so that's our first kind of hint is, okay, well, they have the same molecular weight, pretty similar. And so we might expect them to have similar boiling points. But then if we compare their structure, so formaldehyde now has this ketone group, or aldehyde really we should say. So simplest aldehyde obviously. And so polar, so that means it's going to have dipole-dipole forces. Versus ethane, so just CHs, right? So that's going to be nonpolar. And then it's reflected in the difference in boiling point. So we have -88 for ethane and -19.5 for formaldehyde. So formaldehyde rate still pretty low. And really, you work with formaldehyde in solution, since obviously it boils away. If you were to just try to add it as itself, not in solution. But again, we can appreciate how that permanent dipole-dipole moment leads to the higher boiling point. And so with that, we can see, so again, similar molecular weights. So that's why we're looking at all these compounds. And then we're just seeing how the increase in dipole moment leads to a higher boiling point. And for these, so feel free to use Wikipedia to help you kind of decipher some of these. So we can look, so let's look up propane, for instance. And so again, you want to look at our dipole-dipole moment here. And so Wikipedia should report the dipole moment of most compounds. And so there it is, again, just kind of giving you context. So 0.083 for something that's pretty nonpolar, like propane. And again, okay, we can see that propane has the lowest boiling point. And then we can look at the next one on Wikipedia. Again, just kind of compare. So dimethyl ether. And so we can see, right, we have an oxygen here in the center, so kind of polar. And again, the dipole moment is a good reflection of how polar, if we're having difficulties kind of determining, which is obviously difficult, right? You guys are still learning chemistry and structure and how everything kind of interacts. So I think it's good to look at the dipole moment and give yourself context and compare to other chemicals. And so then you could keep looking it up on Wikipedia. So these dipole moments, And then notice how the ethylene oxide, so we have this little epoxide group here. Actually, I guess we'll show it. And so that tends to be a little bit more polar. Only because of that ring strain, so you can see how this kind of forces the oxygen kind of more up. And so that gives it slightly higher dipole moment, so 1.94. Slightly different numbers, but really close anyways. And again, right, increasing boiling point. And then we can kind of see why acetonitrile has the highest dipole moment. Again, we're just kind of keeping it in context. So let's look up acetonitrile. And looking at it, thinking about the Lewis dot structure, that nitrogen is going to have 2 lone pairs. So that's kind of hinting at our area of high electron density. And again, right, Wikipedia reports that dipole moment. And so this is a pretty high dipole moment. So 3.92. And then we can look up other compounds, kind of put it in context. So for example, if you remember dichloromethane. So this compound, 2 chlorines, 2 hydrogens. So just want to show you all the dipole moment on that. So 1.6 there. So again, you can just kind of place it relatively speaking. So somewhere, you know, along here. So just so you can get a sense of polarities and how things rank. Since that's vaguely what we want to do. And again, right, it's a 100 level class, so we're just kind of learning and understanding where to get this information to. So if you're asked to do this later, right, you can look it up for any compound. Like, I'm not expecting anyone to be an expert on the dipole moment for anything. All right, so that's good to understand. And so now let's look at our next interaction. And so this is the important one. So hydrogen bonding. And so hydrogen bonding is basically kind of a specialized dipole-dipole interaction. And so what I mean by this is it's only in these specialized cases. So oxygen, nitrogen, and fluorine. So maybe highlight that, write it somewhere. You could also, you know, mark it on your periodic table. And so if we look at the location of these elements, zoom in. So of course they're in the upper right corner of your periodic table. So again, fluorine, oxygen, nitrogen, those are the only 3. And so the reason why this is because they are very electronegative. So it mentions that, right? So we have a very electronegative atom. It's bonded towards hydrogen, which if you recall, right, it just has 1 electron. And so then this very electronegative atom pulls that electron towards it. And so it essentially becomes this naked proton, or exposed. And so, right, it mentions the details of it. So again, it has no other electrons. So when that 1 electron is pulled away, the nucleus becomes very de-shielded. So it's just a very extreme, right, dipole-dipole interaction, basically. Again, because of how electronegative oxygen, nitrogen, and fluorine are. And then, of course, this exposed proton acts as a very strong center of positive charge then, again, creating this very strong hydrogen bonding scenario then. And so this is pretty fascinating, or at least I think it is, and its implications. And so this is HF represented here. So our hydrogen, our fluorine, and again, our electrostatic potential map to show us that all the electron density is centered on our electronegative atom here. So again, represented by fluorine. And again, still our same electrostatic interactions, right? Formerly a partial negative and a partial positive, but more extreme. So that's our hydrogen bond. And of course, this has great significance towards life and water. So of course, water obviously is polar. And not only is it polar, but again, right, oxygen, extremely electronegative. So we have that hydrogen bonding phenomenon. And so that also goes back to the structure of ice. Let me see if I can pull up a solid structure of ice. So that's why ice is less dense when it's solid, since those hydrogen bonds, it makes it arrange itself in a nice crystal structure. And then, so while I put that up, so the other significance, of course, is what's our molecular weight of water?
18 grams.
So 18 grams per mole, right? Extremely light. So we would expect it to be a gas if it was not for this hydrogen bonding. And then the other thing to kind of put is, well, it has 2 hydrogen bonds. So make sure you count the number of hydrogen bonds when you're comparing. So here's just a quick representation, again, of the water crystal structure. So we can see how in the solid state form, right, it's giving itself lots of space, and then, right, everything's hydrogen bonded, so there's our water, and then hydrogen bonding, water, hydrogen bonding, so it makes that nice crystal lattice structure, which again takes up more space than water, so therefore ice is less dense. And then if we compare water to ethanol, so here's ethanol drawn here. So ethanol meaning eth for 2 carbons, and then all for alcohol group. And so ethanol just has 1 hydrogen bond. And so, you know, maybe surprisingly or not surprisingly, depending how you look at it, or maybe you're just starting to appreciate the strength of this bond. So alcohol has a slightly lower boiling point of about 78 degrees Celsius for ethanol. And then obviously water, I think you know, is 100 degrees Celsius for the boiling point. So again, pretty cool there for water. And then again, just being able to identify those hydrogen bonds. So our hydrogen bonding with our oxygen of our other hydrogen bonded ethanol there. And so then these are considered the strongest intermolecular attractive forces, so stronger than dipole-dipole or dispersion. And then again, these hydrogen bonded substances have high boiling points, so that's explaining why water is anomalous, and melting points that similar substances cannot. And then again, we're just emphasizing that we're not breaking any bonds, and even though these intermolecular forces are strong, right, they're not as strong as chemical bonds. So even for the strength of the hydrogen, it's only about 5% of a covalent bond. And then again, we can compare boiling points. So just something you might have to do on an exam. So again, I'm not going to make it too tricky, but looking at our basic structures. So this is interesting because we have the same formula. So same mass, right? So dipole, or excuse me, London dispersion forces are the same. Okay, so it's not a molecular weight argument. And so now let's look at the structure. And so our ethanol has our hydrogen bonded to our oxygen. So we have 1 H bond, or 1 hydrogen bond here, versus our dimethyl ether, So there's no hydrogen attached to this oxygen, so it's only polar. So right, we just have our dipole-dipole forces. And we mentioned those are weaker, and again, reflected in the boiling point of -22 for dimethyl ether versus 78 for ethanol. So pretty significant difference there. And then this is another chart that's commonly seen, or there's other similar charts that may include ammonia. So ammonia is not on this one. But basically, so thinking about the main compounds, especially small molecules that we've been discussing, that this would affect. So HF, water, and ammonia all have hydrogen bonds. And so all of these have higher boiling points than would be expected for our trends here. And so like I said, left off ammonia on this chart, but we can see that we mainly have a molar mass argument for these. So as our molar mass increases, boiling point increases, and then water again is our anomaly for group 6. So low molecular weight, but high boiling point again from our hydrogen bonds. And then sulfur, selenium, tellurium, hydride, again they follow just the same trend since no hydrogen bonding. So these will be polar, but again, no hydrogen bonding on those. And so I would expect to see maybe another type of chart too with group 5, since like I said that was missing from this one, and ammonia would be anomalous there. All right, let's look at some surface tension properties. So surface tension is tied to our intermolecular forces. So let's first define our surface tension. So it's just a property of liquids that results from the tendency of liquids to minimize our surface area. And so of course if you've kind of seen water do that and beat up, right, you know that it has strong intermolecular forces, so that's going to lead it to have a high surface tension. And so this is a good quantification of it. So comparing water versus, this is benzene. And so we see again strong intermolecular forces leads to greater surface tension. So IMF is intermolecular forces, and equals greater surface tension. And then, okay, so we mentioned that. And then the other thing that will affect the surface tension is raising the temperature, so that kind of makes sense. So think about what you're doing when you're raising the temperature, right? You're putting energy in, but that's going to start disrupting our intermolecular forces, right, if you're adding energy there. So it could cause disruptions. I mean, that's again how we get to boiling or melting, is adding energy. So we can start to see how that's going to disrupt those intermolecular forces if we increase the energy. So that can obviously reduce its surface tension. And it also mentions, again, increased molecular motion. So that's another way to kind of contextualize it, that it's stretching the surface and not being cohesive. And so, of course, surface tension is also what allows more dense things to float on water. And so I was like looking at this video so we can appreciate go.
Some young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, maybe run on water.
All right, I like watching that lizard. I think he's entertaining. But, right, again, that just goes to show the power of surface tension, and obviously, right, there's many little creatures that take advantage of the surface tension to cross the water. And so again, right, that allows the super dense lizard to walk or float on water, at least temporarily, right, taking advantage of that surface tension. I won't pull it up, but I know there's another kind of video that was making its way on, like, I don't know, TikTok, social media, where, like, people threw a huge rock in the lake. I don't know if anyone saw this. Did you see it? Yeah, and it, like, you can see the surface tension. It's kind of weird. So, yeah, there's cool videos out there. All right, so then a very similar property is vapor pressure. And so vapor pressure is kind of going to be the opposite. So if we have stronger intermolecular forces, then we have lower vapor pressure. And so you can also think about like volatility. So something that is more volatile, right, will have a high vapor pressure. And that means it has weak attractive forces. And so again, I always kind of think about, I don't know, I mean, y'all might be too young to drink and stuff, but I don't know if y'all have opened up like ether too. So ether is another good one that in the summertime it really hits you. So ether sometimes comes in these huge 20-liter drums, has a relatively low melting boiling point. So of course, right, you open it up and kind of get hit in the face with the vapors. And so kind of same thing with ethanol, right, lower boiling point. So you open up your alcoholic drink, kind of hits you in the face, right? So that's the vapor pressure, right? So you're like literally getting molecules coming off. And so again, general trends, the weaker the attractive forces, the more molecules will be in vapor, aka, right, the more you're gonna smell potentially, so that's a good, again, a good indicator of vapor pressure. And again, weaker the attractive forces, higher the vapor pressure, and higher the vapor pressure, then you can use that term again, volatile, so the more volatile the liquid. And so this is a good graph too to kind of think about what is going on. And so let's kind of show what this curve is representing. And so we have to think about vapor pressure and kind of the equilibrium, right, with our atmosphere. And so if we have, like, let's just say this is a cup of water. So even if it's water, right, pretty non-volatile, there's some amount of water that is escaping into the atmosphere. And so we can measure that amount. And so that's what this is showing. So this is our curve, again, for water. And so all we're saying is, okay, we increase our temperature and more molecules are going to be coming out of solution slowly, right? That there's enough energy in one of these to escape until eventually we hit what's called our normal boiling point. So this is, again, how we get to our boiling point is at 100 degrees Celsius. Now it's boiling and our vapor pressure would be equal to our atmosphere. And so all we're saying is at 100 degrees Celsius for water, that now our vapor pressure is 760 torr, again, right, equivalent to all those molecules flying out of your cup at that point. And of course, right, you'd be seeing it as a rolling boil, and that'd be very evident. And so again, kind of same thing for these other volatile substances. So there's diethyl ether. So again, you can think about, I drew it upside down. I like to draw it. So diethyl ether, it looks like a bat. Should draw a little happy bat face on it. So ether, right, we can see that it has an oxygen kind of in the center of 2 carbons, so going to be slightly polar. And again, right, low boiling point, so just dipole-dipole interactions. And again, that's why if you've ever opened up that ether on a hot day, it'll hit you in the face. Didn't they use ether too for like anesthesia back in the day? I think they did. Yeah, so that's also a good reason why it was used, again, historically, since it's pretty volatile, so you can take somebody out with the vapors. And then ethanol, again, like we mentioned, right, 1 hydrogen bond, so a little bit lower in boiling point, and then there's our respective vapor curve. And again, if you've ever consumed alcohol and sniffed different, right, concentrations, you know, right, like Bacardi 151, not that you'd ever want to drink that, is going to be a lot more volatile and kind of hit you in the face versus, you know, like a wine or a beer. Like a beer obviously has much lower percent alcohol, so that's mainly like water. So you can kind of think about vapor pressure. All right, let's go over kind of probably the hardest part of the chapter, I will say. And so this energetics of melting, it's not too hard, it's just a lot of steps. And so we'll go through it all together, the math. And so we've kind of, again, looked at these bits and pieces in lab. And, okay, so when we lose high energy molecules, our average kinetic energy is lowered. And so if energy is not drawn back into the solid, then our temperature of our solid will decrease. And so again, we saw this. So think about, right, the wax or something. So that wax, and we made our melting curve. So of course we took it out of the hot bath, right? We let it cool. And so we saw that it froze, right? It was an exothermic process as that temperature went down, and y'all tracked that. And then of course you remember it hopefully made a little plateau somewhere. And so we'll look at that. And so again, obviously melting requires input of energy to overcome that attraction. And so again, right, the whole point of the lab was to see the state change, where the state change is taking up all the energy. All right, so that's where we're going. So kind of our goal, I'm going to show our goal and then we'll back up to the math bits. So we want to figure out, and again, we're going to go through it with water, but you could be asked to do it in theory for any substance, provided all the necessary parameters. And so we want to take it from a solid all the way to steam up to 125. And so there's different parts of this curve. And so let's go back to this. And so first, we're just going to focus on heating. And so this has to deal with specific heat now of a substance, if you've heard that term, right? Referring to like how much heat does it take to change the degree of a substance. And so this is just given by this equation. And so what drives this equation, though, is usually the specific heat there. So that's what specific heat is. And so it's usually given in some sort of gram per degree Celsius. So that's why this formula, and Q is how much heat we need, and it's going to be in joules. But that's why this formula is such. So we take our total mass, multiply it by the specific heat, which would be provided on an exam. So for water, just to give us context, so it's, remember this number, 4.18 joules per gram degree Celsius. So that's the standard kind of specific heat for water. So again, just kind of providing context. So water in liquid form, so 4.18 joules per gram degree Celsius. And so all we're saying is, again, we're going to figure out how much heat was added with joules, because we're going to multiply it by the grams. So you're going to see grams will cancel, and then the change in temperature, so Celsius, will cancel. All right, so then the problem is, so this only works for our lines here, right? So when we're just adding heat. Once we get to our plateau, we need to look at something else. So now this is going to be heat of fusion. So let's look at this. So how do we treat the plateaus? And I don't know if you want to add, like, I don't know, sorry, I like blanked on the word for not flat, but like linear or increasing part, right? So all these parts where your temperature is increasing. So these parts of the curve, that's where this is relevant. And so now let's look at this heat of fusion, and we should also add to this vaporization, and AKA how to treat the flat parts of our heating curve. And so we have a few different things on here. So let's go through what each of these are. So fusion is referred to the energy required to either melt, or of course if we're going in the reverse direction, freeze. And then if we're just kind of looking at these values, well, this kind of makes sense that fusion would require less energy than vaporization. And of course, you can guess that the heat of vaporization is, right, our energy needed to boil or condense. And then again, obviously it's much, much higher. Other things that we're just emphasizing, so again, if we're going in the forward direction, we're adding heat, so that's again all we're saying. If we're going in the opposite direction, then the heat is negative, right? We have to lose that same amount. And then I'm not sure if we'll encounter this in this class, but just so you're aware, if you were ever asked for the sublimation and you weren't given it, you could just add up the heat of fusion plus the heat of vaporization. So remember, sublimation refers to when something goes straight from a solid to a gas. So usually, right, you see that with CO2 or iodine. So those are the two substances that you would know of that experience that phenomenon. So again, dry ice. And then we saw this with our element display with the iodine. If you remember, the crystals kind of went on the cap. So iodine tends to do that. All right. so now let's kind of go through the math. Again, it's all laid out for us. Is this notebook sharing? Oh, I haven't shared our I don't know what's going on. I might have to export these notes as a PDF. I don't know why they're not wanting to share. Anyway, so we'll go through the math. So it's all on here. But let's kind of walk through it so you feel comfortable if you have to do this on your own, which you will for the exam. All right, so like I said, we want to start at negative 25 degrees Celsius. And eventually we want to get to 125. But we have to start with one leg at a time. And so in this case, right, it's sketched out for you. If it wasn't, you know, you could always sketch this out for yourself. So we need to take it from a solid, right, and we're at our solid state here. And so we're going to take it from a solid from negative 25 up until the melting point. So that's how we know where to stop, right? It's like we have to stop at the state change. And so then the math is presented for us. This is where things get tricky, but I said I'm going to provide this on the exam because you have to look up like every thermodynamic value. And so all we need to appreciate is the specific heat of ice is less than water, so it's only 2.09 joules per gram degrees Celsius. But then once you're given this, so if you're given 1 mole, obviously convert it to grams, so our units match. And then that's all that's done here. And then our change in temperature is, of course, 25 degrees Celsius. And then I would recommend putting it in kilojoules, just so you're not working with super large numbers. So I'll just punch it in so we know that the math is correct. So again, this is in joules based off of our specific heat. So I would report it as such, so 0.941 kilojoules. All right, so now this brings us to the state change. So right, our first state change, so fusion, again for melting. And so again, this is just a standard thermodynamic value you look up. I'll provide it on the exam. This is, again, the only tricky part is watch the units. It usually is presented in kilojoules per mole. That being said, right, if you look it up somewhere else, it could be given in kilojoules per grams or something. So just watch out for the units as usual. But like I said, it'll probably be given in kilojoules per mole. And we have 1 mole of ice. So that was 6.02 kilojoules for the melting process. And so we're just going along following our curve here. So about 6 kilojoules. And so now, right, we're still at 0 degrees Celsius. So important to remember, right, we didn't put any energy into temperature change, just the state change. So now we're ready for leg 3. So now this is the liquid phase, and we want to take it from a liquid at 0 degrees and then all the way right to our next state change. So again, if it's not water, right, you just take it up to whatever the boiling point is. And again, kind of formula really is dictated by what the specific heat is given in. Typically given in, like we mentioned, joules per grams degrees Celsius. So same thing, 18 grams times our specific heat times 100 now. So again, I'll just plug it in so we can see that we agree with the math. And again, that's in joules. I think it's better to be in kilojoules. So 7.52 kilojoules. All right, so we're getting there. And so now, again, another state change on leg 4. So vaporization. So now we're going from a liquid to a gas. Again, it's dictated by our heat of vaporization. So again, typically given in kilojoules per mole. So then we have 40.7 kilojoules for that transformation. And I mean, what's nice about this, how they graphed it, is of course we can physically see how much more energy that takes, right? So again, this heat added is approximately 40 there on our graph. So again, next time you're watching water boil, that's why it takes so long, right? You literally have to add a lot of heat, a lot of energy to it. And so now we can also answer the question, why is steam more dangerous? And so of course now we're at 100 degrees, right? We're at our gas, and now we want to keep this steam going from 100 to 125. And again, just appreciating, right, the energy involved in that. So that means that this steam is just going to have more energy than obviously that, right, that could burn your face or anything else. Specific heat of steam is again less than water. It would be provided, and again, following our formula, so times 18, and then times, so again, we stopped at 125, so 25-degree difference there. So then we should get about 90 joules, or sorry, 904 joules, or 0.904 kilojoules. So we kind of went through that fast, but like I said, it's just a lot of steps. So all of these little portions, right, are kind of repetitive. So again, right, we just need to figure out our specific heat for each leg, and then our heat of fusion, our heat of vaporization for our state changes. Are there questions about that? I just realized I forgot about my demo. All right, we can do the demo really quick, or you can look at it as we kind of head to break. Sorry, I was also need to add I'm trying to add, that's strange. I was trying to add this camera. I thought my computer recognized it. Well, I'll have to troubleshoot that later. I don't know why it's not firing. All right, so you'll just have to look at it, or I might have to do some kind of hodgepodge camera work. So kind of the idea and what we're trying to show is, again, surface tension. And so I don't know if people have done this, like usually you do this maybe in like elementary or middle school, but usually you just do it with water, right? And so kind of the idea is you drop a bunch of drops on the penny, and of course, right, the water beads up. So I have water, I didn't count. And so water is on the left side, and then I want to compare it to, so I brought cyclohexane. So cyclohexane, let me show the structure really quick, otherwise it won't be very relevant. So I didn't want to bring hexane. So hexane is hazardous because of the 6-member chain, and then it's really the metabolic byproduct, which I forget what it is, but it's the 6-carbon chain length that makes hexane just the right length to go between your synapses. So then if you were exposed to a lot of hexane over time, That could lead to neurological issues. But that's cyclohexane. So cyclohexane is just a 6-membered ring, so still nonpolar, so very nonpolar. And so now let's see how many drops. Of course, I missed it. Let me move it away. And, oh, this cyclohexane is still kind of beating. So it kind of starts to spill over. So my cyclohexane is kind of spilling over. And so you can look at them. So probably come up and then you can look at the pennies. So again, the water one you can keep kind of pushing. And so now you can compare, especially if you get like down at eye level. So you can see how the water beads up. Again, obviously, right, that surface tension versus the cyclohexane where it kind of tends to puddle over. All right, so we'll end lecture there, / you can look at this and play with it. So I have droppers if you want to try to add more. And then I'll hand out the quiz. So it's mainly chapter 6, but I did throw a few stoichiometry things on there. The last stoichiometry quiz went pretty well, and then so I just added a few more things for practice and some of the other skills we worked on with stoichiometry. And then again, feel free to take your break or look at this before you look at the quiz. And so online, we'll try to show cyclohexane and water. Don't know how that came out.